All right, example 5 is just another example of using the exponential pattern that we've been talking about. And so I think that you can follow that one along pretty easily in the filled in notes. So I'm going to skip doing that for you here. But I am going to do something where we need to talk about a little bit of a difference. So it says in examples 2 through 5, you did not actually have to solve the differential equation, right? This was the differential equation that we did that general solution to. But the next one, you have to do a separation of variables technique. So it's Newton's law of cooling, which states the rate of change in the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. Okay, so it sounds really, I think, maybe a little intimidating. Okay, but the rate of change in the temperature of an object is directly proportional to the difference between the object's temperature and the temperature of the surrounding medium. So this is going to be some number that we actually know. That's essentially the translation of this. So let's read. It says, let y represent the temperature of an object in a room whose temperature is kept at a constant 60 degrees. This is the surrounding medium. Okay, because the temperature of the room is always 60. So I know that I have dy dt equals that constant of proportionality times y minus 60. All right, so I cannot just jump to what I had before because the difference being that I have this minus 60. So let's go ahead and use separation of variables. So I'm going to have 1 over y minus 60 dy equals k times dt. So just rearranging that. Okay. Also, important to note, we're only talking about y values between 80 and 100 here, if you read the rest of the problem, and so that'll come in handy in just a second. Okay, so when I go ahead and do the integral of both sides, on the left I'm going to have to do a quick u substitution, right, where u would be y minus 60, and dy would be du over the derivative of y minus 60, which is just 1. So this side basically turns into 1 over u du. Okay, and the other side is going to be kt plus c like we've seen in the past. So on this side I have the natural log absolute value of u equals kt plus c. I'm going to go ahead and put it back in terms of u. All right, so I'm going to have ln absolute value of y minus 60 equals kt plus c. All right, now I know for sure for the y values that I have listed for my domain up here that this value is always going to be positive, because if y is only going between 80 and 100, that's going to be positive. So I'm going to go ahead and drop my absolute value, because in this context I know that I will have something that's guaranteed to be positive. All right, and then I can go ahead and do the e to the both sides. E to the natural log is just going to give me this, and on this side I have e to the kt plus c. We've talked about that before, that's e to the kt times e to the c, and we are going to call that a constant a. And so what I have is y minus 60 equals a e to the kt, or y equals a e to the kt plus 60. And this is the model I'm going to use as my general solution. Okay, I still have two things I need to find, a and k. All right, and I'm going to use the information above. So one of the things I know from above, if you read closely, it says y equals 100 when t equals 0. And so I'm going to go ahead and solve for my, as much of this as I can. So 100 equals a e to the, this is going to be 0 plus 60, which means 40 equals a times 1, so 40 must be my a value. Okay, and so as part of my general solution, I have y equals 40 e to the kt plus 60. And now I have to have another ordered pair to go ahead and figure out what my k is. Well, it also says we know y equals 90 when t equals 10. And so I'm going to be able to go ahead and put that in for my actual particular solution. A little bit more complicated now because I have to do the minus 60 first, right? So I'm going to get 30 equals 40 e to the 10k, or divide by 40, so 3/4 equals e to the 10k. Go ahead and take the natural log of both sides, right? So I'm going to get natural log of 3/4 equals 10k, which means k equals natural log of 3/4 divided by 10. Okay, that's probably worth storing. Okay, it does say then what is basically the question is how much longer will it take for the temperature to decrease to 80 degrees? So I'm going to restate that question as, or maybe let's write the actual particular solution. I'm sorry. So my actual equation is y equals 40 e to the natural log of 3/4 divided by 10 times t and then plus 60. All right, so what is t when y equals 80? That's basically the question I'm going to use, or I want to answer using that particular solution. So 80 equals 40, e to that, I'm going to have that k value just be there so I don't have to write it again, plus 60. If I subtract the 60, I get 20, 40 e to the kt. If I divide by 40, I'm dealing with 1/2 equals e to the kt. Go ahead and take the natural log of both sides, right? Natural log of 1/2 equals kt. And you can go ahead and say t is ln of 1/2 divided by that k value that would be stored in your calculator. Okay, and so what we found out is t is approximately 24.0942 minutes. Okay. All right, so it's going to take 24 minutes approximately to cool from 100 to 80 degrees, right? And so if you notice, though, the question, this is a little bit fussy, how much longer, this is important, longer will it take? And so it's already gone 10 minutes to go down to 90 degrees. And so essentially what we have found out is then to get to 80 degrees, right? This is the time it takes to cool from 100 to 80. So it will take 14.094 minutes more to get all the way down from 80 if you're starting at 90. Okay, so that's a little bit of semantics, but I want to make sure that you notice that and look for those wordings in the future.